everybody. Let's talk about torque some more. And to do that, let's look at the example that we did just a few minutes ago. We want to know how much force we have to provide at one of these points in order to prevent the metal bar from falling down. Because the metal bar is connected to a hinge here, it can rotate, and we know that torque matters. Our pivot point is going to be right here at the hinge, and for the moment, let's suppose that we've attached the spring scale here. When we were dealing with forces, we talked about free body diagrams. Free body diagrams represent the object of interest as a single point, and all of the forces are acting on that point. But with torques, we can't do that, because a torque is not just a force. It also depends on how far away that force is from the center of rotation. So for torques, we draw what are called extended force diagrams. We draw the object of interest, and then draw the forces at the location that they actually act. Let's start by thinking about gravity. We know gravity will act on this object because it has a certain amount of mass. But where will it act? Well, because this metal bar is more or less the same everywhere, we can assume that the gravitational force acts at the center of the object. What other force is going to be acting on the object? Well, we know that we've attached the spring scale here, and that spring scale will be pulling to the left on the object. There's one more force in this problem. What is it? Well, the other force is actually the force that's being provided by the second bar. The two bars are attached at the pivot, and there must be some kind of force between them. But for the purposes of torque, it turns out that this force doesn't matter. Why is that? Well, we know that torque is related to the strength of the force as well as its distance from the center of rotation. If a force is acting here at the pivot, how far away is it from the center of rotation? Well, the pivot is the center of rotation, so a force acting here is zero distance from the center. Because it's zero distance, it provides zero torque. Now let's try to calculate what the force of the spring here should read. As a refresher, the mass of this bar is 0.5 kilogram. The length of the bar is 30.2 centimeters. And the distance between the hinge and the location that the spring is acting is 5 centimeters. Let's start by determining what the torque is due to gravity. Our first step when doing this is always to draw the moment arm for the force. The moment arm is just the line that connects the center of rotation to the location of the force. This is an example of when it's good to be clever about which torque equation we use. Remember that there are 3 versions of the same equation. Which one should we use here? Well, if we wanted to, we could calculate theta. It's the angle between the moment arm and the force of gravity. But we don't actually have to do that. Instead, let's use this version of the equation. The torque is equal to the force times the piece of the moment arm that is perpendicular to that force. As always, we can break up the moment arm into 2 pieces, a horizontal piece and a vertical piece. Which of these pieces is our perpendicular? Well, the force of gravity points straight down. So our perpendicular is the piece of the moment arm that points horizontally. And what is the value of this distance? Well, the hinge in this example is basically exactly in the corner. And we know that the force of gravity acts in the very center of the bar. So we should expect that the horizontal piece of this moment arm is just half the length of the bar. And we know the length of the bar. It's 30.2 centimeters. So in this example, our perpendicular is 15.1 centimeters. We can also calculate the force of gravity. We know that the force of gravity is equal to the mass of the object times the acceleration due to gravity. In this case, the mass is 0.5 kilograms, and so the force of gravity is 5 newtons. So the torque is just this number times this number. What about for the spring? Well, in this case, we don't know what the force is. That's what we're trying to find. But we do know that the force is going to be acting perfectly horizontally. But the moment arm is perfectly vertical. It just points from the hinge to this hole. So if the force is horizontal and the moment arm is vertical, then they're already at right angles to each other. And so we can just multiply one by the other to find the torque. But what do we do with these numbers? Well, let's think for a moment about what this object is doing. Actually, that's sort of a tricky way of saying it. The object is not doing anything. It's just sitting there. So if the object is not rotating, then what do all the torques on the object have to add up to? With forces, we said that if the momentum of the object was not changing, then if we add all the forces on the object up, they have to be equal to 0. It's the same thing with torques. If the angular momentum of the object is not changing, then if we add up all the torques on the object, they also have to be equal to 0. So let's just write that out. Now, something to note is we have to be careful about the signs in this case. Typically, we would say that a torque that's trying to rotate an object counterclockwise is a positive torque, and a torque that's trying to turn an object clockwise is a positive torque. Let's look at these and figure out which is which. If gravity was the only torque acting on this object, which way would it turn? Well, this object would just fall down this way. It would start rotating clockwise. So the force of gravity, in this example, provides a negative torque. Similarly, if there was no gravity acting on this object, and the only torque was the force of the spring, then this object would start rotating this way. It'd start rotating counterclockwise. So we have an equation, and the only thing we don't know is what the force of the spring is. If you plug this into your calculator, you'll find that the force of the spring is about 15 newtons. And remember, that's just about what we found when we did the experiment ourselves. But there's one more thing that we can do with this example. One more thing we can figure out. We've seen that the torques on this object are balanced, but what else has to be balanced? Well, the object is not rotating, it's also not moving. So its regular momentum is not changing in addition to its angular momentum. If its regular momentum is not changing, then we know that all the forces acting on this object must add up to 0. What's the force that we didn't account for when we were doing torque? The answer is the force from the hinge itself. We didn't account for it when we were doing torque because it is 0 distance away from the center of rotation, and therefore there's no torque associated with it. But it's still there. It's still a force, and we can figure out what it is just by summing all of our forces. Let's start by summing all of our forces in the y direction. In other words, all the forces that only point up or down. Well, we know that the gravitational force points vertically, but the spring force only points horizontally, so we don't need to consider it here. The hinge, however, has 2 pieces of its force, one piece that points horizontally and one piece that points vertically. So let's write out the force equation for the vertical forces. We have gravity pulling down, and we have the vertical piece of the hinge force pointing up. This is equal to 0 because the object is not accelerating. So what is the vertical piece of the hinge force? Well, it's just 5 newtons. All we have to do is move this negative 5 newtons to this side of the equation, and we have the vertical piece of the hinge force is equal to 5 newtons. What do we get if we do the same thing but in the horizontal direction? Well, in the horizontal direction, there are again only 2 forces acting. We have the force of the spring, which is pulling to the left with 15 newtons, and we have the horizontal piece of the hinge force, which is pointing to the right. So how strong does this horizontal piece of the hinge force need to be? Well, it just has to be 15 newtons, because it has to counteract the force of the spring. So the vertical component of the force from the hinge on this bar is 5 newtons, and the horizontal component of the force on this bar from the hinge is 15 newtons. This kind of problem comes up all the time in thinking about torques. If we had started this problem by trying to balance the forces like we just did, we would have immediately run into a problem. We could have found the vertical piece of the hinge force because we know the other vertical force, it's gravity. But we could not have figured out the horizontal piece of the hinge force, because in order to find that, we first had to know what the force of the spring was. And the only way for us to figure out what the force of the spring was by looking at torques. So it's very common to have this type of problem. By picking your pivot point correctly, you can eliminate one of the forces from the torque problem. Doing that will allow you to find another one of the forces. Once you've done that, you then have all the information that you need to add up all the forces and set them equal to 0. Doing so in this problem allowed us to find this other force, the force from the hinge. This state is called static equilibrium because the object is not moving and both its forces and its torques are balanced. Next EL, we're going to start to see more examples of static equilibrium, and we're going to continue to develop our problem-solving skills for these kinds of problems.